Hello and welcome. In this video, we'll be covering the concept of the unit circle and how to memorize it. My goal for you by the end of the video is to be able to solve special right triangles and recognize their existence on the unit circle, to be able to convert forwards and backwards with degrees and radians to degrees, and most importantly, to actually be able to completely fill out the unit circle. So the first thing I'll discuss is special right triangles, which are the 30-60-90 triangle and the 45-45-90 triangle. These hopefully are something from the past where hopefully we have some sort of connection to what the ratio of the sides are. For the 30-60-90 triangle, we always base everything upon the short leg. The short leg, if we just define it to be some variable, I'll just use W, the hypotenuse will always be double whatever that amount is. The longer leg, on the other hand, this bottom one, is always going to be that W, or the short leg side, times the square root of 3. For the 45-45-90 triangle, the two legs for this one actually are congruent to one another. So if I just define one of them with a variable, I'll use a different one this time, I'll say t. The other leg also then must be t. And then the hypotenuse happens to always be the square root of 2 times whatever that leg length is. So in this case, t times the square root of 2. So for each of these, with reference to the unit circle, the hypotenuse is always going to be like a radius, and you'll see this on the next slide when I go through it. But each of these, if I go ahead and just say, let's let the hypotenuse for each of these have a value of 1, we should be able to solve the other two sides using or taking advantage of those ratios. So if we know that 1 is in the same position as 2w, I should be able to solve for w just by dividing by 2 and find that the w value for this triangle would have to be 1/2. And now that I know that value, I know that the longer leg is just going to be that value times the square root of 3, and square root of 3 times 1 on top would just remain square root of 3, and then over the 2. For the 45-45-90 or 45-45-90 triangle, it's going to be very similar start. I'd set the 1 equal to the t times the square root of 2. With this one, I would have to divide by the square root of 2. And that would then give me t is equal to 1 over the square root of 2. And usually at this point, we would go ahead and rationalize that denominator and go ahead and multiply the top and bottom by the square root of 2 to then give us our final value of t for this scenario is going to be 1 times the square root of 2 on top, so square root of 2, and then square root of 2 times the square root of 2 would just turn into a single 2. So at this point, we know that the two legs for this one are square root of 2 over 2, as well as another square root of 2 over 2. Now, as far as some of the other things we may need to do with the unit circle, converting angles, if we need to ever go from degrees to radians, we essentially just take whatever our angle is and we multiply it by pi over 180. To go the other direction from radians and turn it back into degrees, we just take our angle in this scenario and multiply it by the reciprocal, so in this case it would be 180 over pi. And each of those would be kind of a backup plan. If you knew what the degrees were, you could come up with the radians, or vice versa when it comes to the unit circle. So since this one has a 30-degree angle right here, we could use our degrees to radians conversion and say that 30 degrees times pi over 180, if we go ahead and simplify that, we would notice that 30 degrees is equivalent to pi 6th radians. We could do a similar thing with the 60-degree angle that we see right here. So if this one's our 60-degree angle, we could do 60 degrees times that pi over 180 and find that every time 60 degrees happens, we know that that would be pi thirds. Again, if we reduce the 60 and the 180, it would turn into a 3 in the denominator. The only other angle really that we have that we might want to worry about is over on the 45-45-90 triangle, which is the 45-degree angle. So once again, we could go ahead and try and convert it. 45 degrees times pi over 180, and that would be able to turn into, if we were to reduce, a pi over 4. And I suppose we do technically have one more angle we could convert just to see what the radian measure will be for that. Let's go ahead and talk about 90 degrees. 90 degrees, if I multiply by pi over 180, a 90 over 180 would reduce to a 1/2, so this would just turn into pi halves. So we'll notice as we move forward that this 60 and pi 6 are going to connect with each other. The 60 degrees and pi thirds will connect with each other on the unit circle. Same thing, 45 and pi fourths, as well as 90 with pi halves. There will be a little bit easier way for us to have this down that I'm going to talk about, but that's a good backup plan. If you know what the degrees are, you can always convert it into radians just by following this particular formula down here at the bottom. So you may be wondering why we even talked about the special right triangles, but when you look at any unit circle, you'll notice that in each quadrant you have these 3 rays that come out from center to the circle, that if we were to take each of those triangles, say like this 30, 60, 90 right here, notice that it actually fits this first ray that comes out. And if we think of what that should mean to us, we could essentially then take the values that we just solved for. If we know that the radius here is a value of 1, we then know that the x-coordinate, or the horizontal, is going to be the rad 3 over 2, whereas the vertical component, or the y value, would be 1/2. So we could technically say over here that this has an ordered pair on the unit circle of rad 3 over 2 paired with 1/2. And we could do a similar thing now with the triangle that's the other 30, 60, 90. Notice that one fits that third one. And at this point we could then label that using the same general idea of the horizontal component with this one now is the 1/2, whereas the vertical component now is the rad 3 over 2. So I could then say that this ordered pair has the x value of 1/2 and the y value of square root of 3 over 2. Again, if you think in terms of which one was longer, the y value for this triangle was longer than the x value, whereas it was completely flip-flopped with the other one. Now if we go to the last triangle, the 45, 45, 90, notice that one fits this middle one. And so with that one we could then do another similar step where we would know that the 2 legs are square root of 2 over 2 from the previous slide. So if that's the square root of 2 over 2, and then this length over here is also the square root of 2 over 2, we could then say that the ordered pair for that point that's actually on the circle would be the square root of 2 over 2 paired with another square root of 2 over 2. So as you can see, our options here with our x's and y's, if we include this point over here of 1, 0 and 0, 1, our options from least to greatest are going to go 0, then 1/2, then square root of 2 over 2, then square root of 3 over 2, and the final largest value would be 1. Now, a pattern that we can hopefully kind of see right here is each one of these we could say is technically over a 2 and also inside of a square root. It just happens to be that some of these values can reduce, but when we get to the last one, notice that it would technically be like the square root of 4 over 2, because that would reduce to 2 over 2, which is a value of 1. So kind of what to take away here is notice that the pattern goes 0, 1, 2, 3, 4, all inside of radicals in the numerator, and every single one of them is over 2. It just happens to be that the square root of 0 over 2 I could simplify and just call 0. The square root of 1 is 1, so the square root of 1 over 2 I could really just say is 1/2. Square root of 2 over 2 doesn't reduce, square root of 3 over 2 doesn't reduce, and then the last one, square root of 4, is 2, and 2 divided by 2 would equal 1. So really it's just these ones in the middle that we need to kind of see what the pattern is, and we can just think in terms of, am I going to be counting up from 0, or am I going to be counting down from 1? So if we think in terms of what we see here on the, I guess, part of the unit circle that we currently have on here, if we look at just the x values starting at, I guess, what would be considered standard position, which is the positive side of the x-axis, its x value is 1. So what we're going to do is do the count down idea. So notice the x values as I go around the circle, count backwards 3, 2, 1 until I get to 0. The y's, on the other hand, start at 0, so that means they're actually going to be counting up. So notice it goes from 0, next one is 1, next one after that is 2, followed by 3, and then the final thing is 1 whole. And everything in the quadrant itself has denominators of 2. So kind of taking advantage of that pattern of it just either goes 3, 2, 1 or 1, 2, 3 inside of that quadrant. If you just think in terms of is the x value larger or is the y value larger, that can kind of help with what should I start with. But you can also go back to what's happening at the first point that I'm going, and then as I go around the circle, what's supposed to change. Should my x increase or should my y increase? What should be the logic of what's going on? And you can follow this into the other quadrants. If you needed to get there, just realize it's going to follow the same pattern. It's just now going to have some negative signs get involved. So now let's go ahead and get on to the actual filling out of the unit circle. So the easiest thing usually to fill out that most people have success with is the degrees. So we'll go ahead and start with our degrees. Standard position is always going to be start at the positive side of the x-axis. So that's always going to be where our 0 degrees is going to go. If we know a full circle is 360 degrees, we could also label that same angle as 360 on this line. And if we think in terms of how could I easily fill this out, well, if we take advantage of the 30-60-90 as well as the 45-45-90, we could just count by 30s, and then that would skip everything except for it would skip all of the 45-degree angles. So if I just went from 0 degrees, the first one in that first quadrant would be 30 degrees, skip the middle one because I'm going to add another 30 degrees, which would take me up to 60, and just continue that same pattern. So it would be 90, followed by 120, 150, 180, 210, 240, 270, 300, and 330, and then the last one confirms the 360. So the only thing we skipped were all of those middle ones, so that's where we can go back and think, well, that's actually the other triangle that we had, which was the 45 degrees. So if this was 45 degrees, add another 45 degrees, that would take me to 90. Add another 45 degrees, that would give me 135. Go to 180 after that. 45 more than that would take me up to 225. 45 more is 270, and then 45 more than that would give me 315. An alternate way that you could get those middle ones is just think that that's technically 30 degrees to 45 degrees. That really was just adding 15 degrees. So you could just go to whatever the previous angle is and just add 15 to come up with each of those. So 120 plus 15 gives us the 135, 210 plus 15 gives us 225, and 300 plus 15 would give us 315. So it's just a different way that you could do the same thing without having to do as much addition. With larger numbers, it's a little easier to just add 15. The next thing for us to do is to now fill out the radians. So what we can take advantage of with this now is if I know that radians, or it takes 2 pi radians to go all the way around, we could say that the beginning is 0 radians, but also 2 pi radians, just like we did with the 0 degrees and 360 degrees. And with this, we can really do this more thinking like cut in half. So if 2 pi is all the way around, hopefully it would seem reasonable that halfway around is pi. Half of that up here where 90 degrees is must be half of pi. And then half of 90 degrees, which would be 45 degrees, that would turn into half of a half, which would be a quarter. Now we can also look at this like pieces of a pie, where if we said how many of this size of pieces of pie do I have? Well, if I said that's 1, there's 2 here, 3, 4, 5, and 6. If it takes 6 of those pieces to equal the pi that we see right here, hopefully it would seem reasonable that this must be pi sixth, or 1/6 of pi. So if we kind of take advantage of knowing that that first one is always pi 6, which we also did earlier by converting 30 degrees into radians, we could have also done it that way. We can then actually just add pi 6 over and over and reduce any fractions that we have, just like we did when we added the 30 degrees. So pi 6 plus pi 6 would be 2 pi 6, but a 2 over a 6 would reduce down to a pi over 3. Another pi 6 on top of that would take me to 3 pi 6 right here, but 3 pi 6 can reduce down to pi halves because 3 over 6 reduces to 1 over 2. So if that one was 3/6, the next one would be 4/6, but that would reduce to 2 pi thirds. The one after that, if I add another pi 6, that would take me up to 5 pi 6. That one doesn't reduce. One after that is 6 pi 6, but 6/6 does reduce to 1 whole, hence why that one is pi. The following one after that would be one more than 6/6, so that must be 7 pi 6. One after that would be 8 pi 6, but 8 over a 6 actually can reduce to a 4 over a 3, so 4 pi thirds. After that, I'd have 9 pi 6, but 9/6 can reduce to a 3 over a 2, so 3 pi halves. 10 pi 6 would be the next in the sequence, which can reduce down to a 5 pi thirds. And then 11 pi 6 would be the next one, which doesn't reduce, and 12 pi 6 would reduce to 2 pi. So notice we can do a similar step. Again, it's skipping the middle ones, just adding 1 pi 6 each time and reducing any fractions. The ones in the middle, we really can just think of it as like we're adding fourths. So 1/4, 2/4 reduces to 1/2, so it confirms that one. 3/4 would be the next one, so 3 pi 4 is the middle angle in the second quadrant. 4/4 would be over here at pi. 5 pi 4 must be the next one. 6 pi 4 would reduce to 3 pi halves down here, so that one's confirmed. And then 7 pi 4 for our last one, and 8 pi 4 would again confirm the 2 pi that we have. A different way that we can actually go through and do this, though, is to kind of take notice of where are all of the denominators of 6. Well, all of the denominators of 6 are the ones closer to the x-axis, whereas all of the pi 4 are in the middle, and all of the pi thirds are closer to the y-axis. So if we kind of take note of that, what we can also start doing is looking at each quadrant and going, how is the numerator related to the denominator? Well, in the first quadrant, the numerator all has just 1 pi, but then the coefficient changes once I get out of that quadrant. And notice if I'm getting closer to 1 whole pi, that it would hopefully seem reasonable that the fractions that we see in the second quadrant are going to have numerators that are less than the denominator, and it happens to be these are always 1 less. Once I pass 1 whole, then that should now be an improper fraction, but it should still stay relatively close to a value of 1. So notice in the third quadrant, these ones are actually 1 more than whatever the denominator is. And then once we get closer to 2 whole would really be like double the denominator. So in this case, it's going to be double whatever the bottom number is or denominator is, then minus 1. Or you could even think of that as it's 1 less than double. So if we kind of go through each one of them, notice if I were to look at 5 pi 6, the numerator in that area needed to be 1 less because I hadn't passed pi yet. Once I got past it, then it was 1 more than the denominator. And then once I get over to like 11 pi 6, that would be something where it's 1 less than double. Well, double 6 is 12. Take away 1, that would be 11. And notice we can get those numerators a slightly different way. So now that we have all of our angles marked, we can now go ahead and start taking advantage of the 30, 60, 90 as well as the 45, 45, 90 triangles and start filling in some of the actual ordered pairs that lie on the circle itself. Now the ones that are easiest, because the unit circle has a radius of 1, as we can see from the equation of the circle here, this then means that the radius would equal 1. I can fill out all of the ones that are on the axes themselves relatively easy because the x value at this first point needs to be a 1, the y value needs to be a 0. Move up to 90 degrees, I know that the x value now is 0 and the y value is 1. Going to the one at pi, I know that my x needs to be going left, so it would be negative 1 paired with 0 for y. And then the last one at 270 here, I could say that the x value is 0, but now my y value went down, so it's got to be negative. At this point, we then go through and just take advantage of the pattern that we mentioned before. We know all the denominators are 2's, so we can go ahead and just fill in 2's for every denominator that's actually in each quadrant itself. And if we go through and do that, the only thing we'll have left to do is figure out what should go in the numerators. So if we go ahead and start going through the first quadrant, notice the x value was starting as high as possible. It's starting at 1. So the x coordinates here are going to count backwards, 3, 2, 1. And then everything should get a square root, but putting a square root on 1 would simplify to a 1, so I really don't need to put a square root on that. So it's really only going to be the 2's and 3's in the numerators that I'll need to worry about square roots with. The y values, on the other hand, start at 0, so they must need to count up. Hopefully that makes sense, because as I go around the unit circle or along the circle, the y value should increase as I go towards 90 degrees. So this is going to go 1, 2, 3. And again, the 3 and the 2 that I write in the numerator always get square roots. Once I have this one, I can technically actually start reflecting towards other quadrants, but I can also just consider the pattern of what we're doing. We just know that some negative signs are going to have to get involved. So if we go again with the x values, I'm starting at 0, I'm going to head towards -1, so it means it's going to need to essentially increase 1, 2, 3. 2 and 3 get square roots. And in this quadrant, all of the x values technically are negative, so I just throw negative signs in front of each of those. The y value starts as high as possible, so it's going to count backwards, 3, 2, 1. Throw the square root on the 2 and the 3, and it's positive in this quadrant, so I can go ahead and keep those as positive values. And then I just continue that same pattern as I go around. So my x's in the next quadrant should count down, so 3, 2, 1, because I started at the higher value. In this case, it started technically at -1. Square roots go on the 2 and the 3, and everything in this quadrant is negative, so I'll just throw negatives on the x's as well as the y's, so I can go ahead and maybe get my negatives on the y values already. The y values in this scenario, though, are going to count up 1, 2, 3 because they started at 0 right here, and then the 2 and the 3 once again get the radical, and then make sure that the negative sign stays outside of the radical. Going on to our last quadrant, our x value starts at 0 at 270 degrees, so as I continue around it should count back up, so 1, 2, 3. 2 and 3 get the square roots, and this is a quadrant where x values are positive, so those are all going to be positive. The y values are negative, so I can go ahead and set up my negative signs, and these are going to go 3, 2, 1. And then again, the 2 and the 3 both get the radical. So notice now we have all of the ordered pairs filled out for each one of these. So what's the point of having all of the x's and y's? Well, the x's are all the cosine of each angle, or the cosine ratio of each angle. So for example, like cosine of 30 degrees, we would just look at what the x coordinate is for that ordered pair, and we'd be able to say that cosine of 30 degrees is a ratio square root of 3 over 2. And the y values for each of these is the sine of that, or the sine ratio for that angle. So another example I could do is maybe like the sine of 120 degrees. I would just identify where 120 degrees is, and then go ahead and identify the y value, which was square root of 3 over 2, and know that the sine of 120 degrees is that ratio, square root of 3 over 2. The other common function that we can get from the unit circle is what's called the tangent function, and the tangent really is just the ratio of the y value divided by the x value. So each one of these, there's only so many options that I can do when it comes to dividing those. Remember, with division and fractions getting involved, we do the invert and multiply. So if I were to take this ordered pair at, say, like pi 6, notice the possible ratio I have is 1/2 being divided by square root of 3 over 2. But again, dividing by a fraction, I could just invert and multiply, so it would be the same as multiplying by 2 over the square root of 3. The 2's, you would notice, can cancel, and this would then turn into 1 over the square root of 3, which I can then rationalize by multiplying by the square root of 3 on top and bottom, and find that this is the square root of 3 over 3 for that particular ratio. So I could then say, okay, well, this ratio for tangent is square root of 3 over 3. The next one at 45 degrees is a lot easier because the x value and the y value are identical, and so anything divided by itself, notice that would turn into a value of 1. The next one that's a little bit more complex would be the one at 60 degrees, which in this case would be the square root of 3 over 2 being divided by 1/2, which again is the same as multiplying by the reciprocal of 1/2, or 2 over 1. Once again, the 2's in this scenario cancel, and we notice that this would have a ratio of square root of 3 over 1, which I wouldn't have to rationalize. So that particular tangent I could say is square root of 3. So now that we kind of see where those ratios are coming from, if you just spend a little time memorizing, notice we have a bunch of 3's and then we have the 1 whole. The 1 whole should be the easiest one out of those to identify because it's when the x and y value are identical. If I go into other quadrants, I just have to worry about negative signs potentially. So if we went over to say like 3/4, the x and y are the same, it's just one of them is negative, so that one must be -1. If I go to 5/4 in the third quadrant, the x and the y there are also the same, but they both are negative, so this would be back to a +1. And then if we go to the tangent of 7/4 over in the fourth quadrant, we could see that those are the same x and y values, but again, there's only one negative sign, so it has a value of -1. All of the other ones, if we think in terms of tangent, technically, since it's a y over an x, we also could consider this concept right here, the idea of slope. And hopefully we know that the steeper the slope, or the bigger the slope is, the steeper the line should be. So out of the last two options that I have, square root of 3 compared to a third of square root of 3, square root of 3 should definitely be larger. So each of these steep lines in each of these quadrants are going to be ones that have square root of 3. It's just if it's falling down the page from left to right, I know it needs to be negative. So this steep one in the second quadrant would be negative square root of 3. The steep one in the third quadrant, since that now is rising again, that would be positive square root of 3. And in the fourth quadrant, the steep one needs to be the negative square root of 3. Which then leaves all of the not so steep ones. They must equal the rad 3 over 3. So rad 3 over 3. But again, everything in that quadrant looks like there's negative slopes. In the third quadrant, everything is positive slopes. In fourth quadrant, everything is back to a negative slope. So that leaves us with just the ones along the x-axis and the y-axis. Well, a horizontal line slope, hopefully we've always known to have a value of 0, so the two tangents at 0 and pi, or 0 and 180, are going to have a ratio, or tangent ratio of 0. The other ones, vertical line slopes, hopefully we remember we actually used a word undefined to describe that. So the two along the y-axis, we actually put undefined right there. And at this point, we have the entire unit circle filled out, where now I can evaluate any of the three basic trig functions, sine, cosine, or tangent, just by looking at the values that I see. So an example being, if I wanted to identify, say, like the cosine of 150 degrees, I would just go to 150 degrees, identify the x value, because again, x is what cosine relates to, when we would see that the actual ratio there is the negative square root of 3 over 2. I also have the ability to do tangent of any of the angles, so if I wanted to do like tangent of 300 degrees, I just would identify where 300 degrees is, look at the tangent ratio I've identified, and we would know that the tangent of 300 degrees can be replaced with negative square root of 3. Hopefully this is something that you found useful. Hopefully this helps you in being able to fill out the unit circle just from memory. But if you have questions, just reach out to your teacher, and I'm sure they're more than willing to help. Appreciate you taking the time watching the video.